Yeah, so the organizer, so my original plan was to give a talk about a recent work, but then the organizer asked me to actually give a broader overview talk. So that's what I'm gonna try to do today. So it's always challenging to give a talk about bounded arithmetic. A lot of people don't know the basics, so you need to spend some time on it and so on. So I plan to cover the very basics, but because of that, I will only be able to kind of give you a guide for some of the existing results. So this will be like a very high level presentation. Okay, so complexity theory. So for this talk, we are interested in the big major open problems. And in particular, we are interested in trying to understand this huge gap between the best known upper bounds and the best known lower bounds for like problems of interest. So we're going to be looking at the mathematics of complexity, which now studies not the complexity of problems, but how difficult it is to prove theorems about the complexity of problems. Okay, so that's about mathematics. And the holy grail of this area, if possible, would be to specify or to figure out a theory T that is able to prove all known results in algorithms and complexity, and then to give us an excuse why we haven't succeeded so far, right? And then we show that in this theory, the major open problems cannot be settled. Okay, so these results we aiming for that are unproved at all. So this would be the ideal result if indeed these results, these complexity questions are improvable. And of course, if we could do this, this would be like a major development in mathematics and computer science at the same level of some of these previous classical independence results. So we are so far from saying anything like this. We don't even know if it's true. As far as we know, we're just missing some simple ideas to solve these major problems. So what we're going to do in this talk is to relax this to a much less ambitious goal. Okay? So we aim to identify a theory that can at least formalize most of the known results in algorithms and complexity, and then perhaps conditionally to show that some of these major problems of the interest cannot be established in this theory. Okay, or maybe establish that in the theory. So we're trying to understand like the proof complexity of these questions. Okay, and the focus will be on bounded arithmetic. So these sub-theories of Peano arithmetic that have been widely investigated for a few decades now. And they are able to formalize not just basic, but also some advanced results from the area. Okay, so so what is bounded arithmetic? So these are theories that aim to manipulate concepts from a given complexity class. Okay. And some of the important examples here are the theory PV for polynomial time reasoning, Buss's theories SI2 and TI2, where the reasoning corresponds to the different levels of the polynomial hierarchy. And also, yeah, Habig's sphere APC1 that is connected to probabilistic polynomial time reasoning. Okay, so here's just an example of some of the theorems we can formalize in these theories. So we can prove both upper bounds and lower bounds. So for instance, we can formalize randomized matching algorithms in APC1. So what do I mean by formalizing an algorithm? So when you showing that a problem has an algorithm, you prove two things. One, let's say you show it runs in polynomial time. And the second piece is you prove that it's correct, right? That for every instance, say it outputs one if and only if there is a Hamiltonian cycle. So we're interested in also formalizing the proof of correctness in the theory. Okay, so that's what I mean by formalizing the upper bound. So another example, this theory PV can establish the PCP theorem. And this theory APC1 that I mentioned before can also formalize some of the classical circular lower bounds. For instance, lower bounds against AC0 and lower bounds against monotone. Okay, so here is the plan for the talk. So I'm gonna introduce the basic theories. And then I'm gonna survey some unprovability results from the last 5 or 10 years both in the direction of upper bounds and lower bounds. And then if I have time, I'll tell you about some new results on the reverse mathematics of lower bounds. Okay, so my introduction to bounded arithmetic will be brief, but I would like to guide you to this really nice talks by Sam that gives like a better introduction to bounded arithmetic, and also to his survey on connections between bounded arithmetic and proof complexity. I think these are great resources if you're interested in learning more about this area. Okay, so what are these theories really about? So they are sub-theories of Peano arithmetic. And the key feature of these different theories is how much induction you have on them. Okay. So we prove things by induction all the time. And I would say that for most of the talks you have seen here, we saw several arguments by induction. We not always make it explicit, okay? But pretty much everything we're doing, like if you're defining something, there's some recursive definition. We're doing things recursively. We're proving things by induction. And so this series, we're gonna tell you like in which cases you can use induction. And more specifically, you'll be able to apply induction when you can formulate the induction hypothesis with a predicate that can be checked in some complexity class. Okay, say your induction hypothesis is some condition that you can check in polynomial time. So this will correspond to one of these theories and so on. Okay, so to formalize this, here I have two examples. So PV has induction for what is called sigma B0 formulas. S12 has what is called polynomial induction for sigma B1 formulas. So let me tell you about what are these classes of formulas and what are these two induction principles. So to do that, I need to tell you another important piece of information about bounded arithmetic, which is this notion of bounded quantifiers and then the corresponding bounded formulas. So roughly speaking, a bounded quantifier is a quantifier where we'll be quantifying over sets of size 2 to the poly n. Okay, so think of it as some NP predicate. So that is an existential condition over some set of size 2 to the poly n. So these are like bounded quantifiers we'll be using. And the class of sigma bi formulas are those formulas where we have I blocks of alternating quantifiers, okay, starting with existential. So in particular, when we talk about S12, we're talking about sigma B1 formulas. So this will be bounded existential quantifiers. So that corresponds to NP predicates. Okay? So in particular, S12 will have a form of induction where the induction hypothesis is an NP test. So we also have to introduce what is called sharply bounded quantifiers. So now the quantification is over small sets of size poly n. So that's how you should think about these quantifiers. So whenever you quantify, you not only have some term, but you actually take the length of the term. And the length is sort of like a log operation. Okay, so it decreases the size of the universe by log. And the classes of sigma B0 formulas are those that only have sharply bounded quantifiers.
You
Yes?
don't allow sharply bounded quantifiers in general sigma IB formulas for free, do you?
Yeah, I'm kind of like sweeping under the rug this kind of thing.
Okay, good.
Yes, thank you. So yeah, so sigma B0 formulas, they will have these quantifiers for domains of size poly n, and in particular, we can just evaluate them and decide the predicate in polynomial time. Okay, so in particular, the PV theory, we have a form of induction for predicates that can be decided in polynomial time. Okay, and finally, let me define the induction principles. The int principle is the usual one, and there's also the polynomial induction, where now when you move from, so you should really think of this induction step from x over 2 to x as you talking about objects in binary notation. Now you're proving something for objects of n-bit complexity, you can reduce to objects of bit complexity n-1. Okay, so we're doing induction over the binary complexity of the objects. So any questions so far? This was like high level. It's not fully formal. I'm giving you an intuition for this. All right, so in the next slide, I'm gonna tell you about the actual definition of PV. So PV is one of those definitions where you look at it once and you pray that you never have to use again in your life. It's ugly. But fortunately for us, we're gonna use an equivalent definition, and this was introduced by Emil Habling. So let me tell you about this equivalent formulation of PV. Okay, so we are talking about first order theories. In the usual sense, the intended model for this theory is the set of natural numbers and the usual operations. So everything is going to be about natural numbers, but we can easily map numbers to strings and strings to numbers. Okay, we will have these polynomial time maps in the theory. So we'll still be able to encode our statements we care about graphs, matrices, computations, and so on. Okay, so that's the language. We have the constants, some function symbols. Over there is the intended meaning of the symbols. Here is more detail what I mean by bounded and sharply bounded quantifiers. So these are really just abbreviations for the actual subformulas, okay? It's not that we're using some new quantifiers inside the theory. These are like the standard ones. These are just abbreviating an expression. And finally, here's the full definition of PV in its glory. So we're going to have the induction principle for all sigma B0 formulas. Okay. And we have a finite set of axioms about these function symbols, like the basic properties of the function symbols. Okay. And from these basic axioms, you can deduce all the usual properties of plus, multiplication, and so on. Okay, so that's the definition of PV. It's a first order theory for the natural numbers. It has some limited induction. It has some finite set of axioms about the symbols. Any questions about the definitions? Yes.
Okay, the only function symbols in this are the basic function symbols that you listed, right?
Yes.
But if I want, I can add for free, quote,
Yeah.
function symbols for every function in P time, right?
Yes. Thanks, Marco. Yeah, that's my next slide.
Oh, okay.
So we want to. Yeah.
Sorry, can I ask a question before you keep going? So this is the same base theory as you would normally equip like SI to with?
Technically, you might need a slightly different set of basic axioms.
Okay.
But let me not get into that.
Okay.
Okay, so we want now to talk about complexity theory in these theories. And as Marco was pointing out, maybe that's not the most convenient language, right? You only have plus, multiplication, and a few basic operations. So you want a more convenient language to formalize your statements. And this is something that can be adjusted. So I'll just mention some facts now without actually explaining them. But this theory, as I defined it, what we can do is we can use the existing formulas to define new expressions, to define new predicates, right? By combining these formulas. And you can use that to introduce more complicated expressions, capturing any polynomial time computation. Okay, so more formally, this is known as you can define the polynomial time computations. So I'm not getting to this, but it's some standard construction where you just build these more complicated expressions and you give them a name. So this is a new function symbol. I'm just going to add an axiom to my theory saying for this expression, I'm going to call it this symbol. And then you can show that the theory will prove what you hope to have for these new function symbols. And the most important property is that as you introduce these new definitions, the theory can also prove that you can now use the new function symbols in the induction, okay? And in particular, you'll be able to do polynomial induction for open formulas with these new function symbols. And we will be use this at some point in the talk.
But you can't necessarily do induction on formulas in the new language, is that?
Yeah, you can also do it, yeah.
Oh, okay.
That's a theorem of PV that you will also be able to do the usual induction, yes.
I think I understand now Robert's question. In V0 one starts with AC0 class, this starts PV, it's way higher.
Yeah, so I'm now talking about weaker theories. I'm starting with polynomial time theories.
Thanks.
Okay, so good. So in practice, what it means is that we can use any polynomial time function when we express our statements. Okay. And so let me just give an informal example. So suppose we want to write a sentence saying, here is a language in P, and this language has circuits of size n to the k. So how would I write down such a sentence? So you would have an expression of the form, for every n, so we're quantifying over some object, and we take like the bit complexity of this object, so that's our little n. Now we're gonna write in the sentence, there is some circuit C, some object, and the length of this object is of size, say, n cubed. And now for every n bit string x, C of x equals L of x. Now let's just parse some of these things. So the last condition, C of x equals L of x. So because I have this circuit, so I can evaluate it in polynomial time. So there's some polynomial time function symbol that can express C of x equals L of x for us. That's in the language of the theory. And we can also do checks like, is my object x an n-bit string or not? And I can check that in polynomial time. So, and then you can adjust this informal expression here into an actual formal statement in the theory. Okay, but things can be done naturally because we have access to any polynomial time predicate as a function symbol in the language.
It will be sigma 2, right?
Can you say?
Or it will be sigma 2 formula.
This one will be a for all exists for all. So for all sigma
But
b2.
I remove. Oh,
I'll say for all sigma b2.
Is L here?
L is some fixed language in P. And in particular, you already have a function symbol for L in the language. It's a polynomial time computation. More questions? All right. There's another theory that is important called APC1. It stands for approximate counting. And here, the only difference is that we take this PV that I have just introduced. By the way, I'm using PV and PV1. These are the same thing. So we take this theory PV we have just discussed. And now we add a collection of axioms for the dual weak pigeonhole principle. So what do I mean by dual weak pigeonhole principle? So for every function symbol in the theory, we add an expression saying, when I view this function symbol as a map from 2 to the n pigeons to a slightly larger number of pigeons, then there's an empty hole. Okay, and for every function symbol in the theory, I add this axiom, and this becomes APC1. So it's an extension of PV, where we also have the dual weak pigeonhole principle for all polynomial time functions.
little n is the bit size of integers that you are dealing with.
Yeah, I'm kind of glossing over these details, but yes, you would.
It's the most important detail. It's a whole business.
Yeah, so since Sasha is concerned about this, let me,
Oh, very concerned.
if I have the actual definition. Okay, so this is the actual definition. So this is for the weak pigeonhole principle, but the size are similar. So
It talks about integers. No,
yeah, we talk about integers.
no second order
Yes.
business.
And yeah, so we capture this in the natural ways, but let me not get into this kind of details for that.
This is the injective.
This is the injective, the weak injective principle. All right. Yeah, and APC1 is known to lie in this hierarchy that I mentioned before. So, any questions about the APC1? All right, and okay, so I define APC1 as just having this extra principle, the dual weak pigeonhole principle. But there's much more to this theory. So the reason it's defined in this way is because just with this extra principle, it allows you to do all kinds of interesting things, like introducing a notion of probability, where we can actually formalize probabilistic arguments in bounded arithmetic. So a lot of probabilistic combinatorics can be done in this theory. And in particular, the theory is able to formalize circular lower bounds, like the monotone circular lower bound for click, AC0 lower bounds, and so on. Okay, so that's a very nice theory to actually formalize many things we care about in algorithms and complexity. And Emil has some really nice slides about the theory explaining these things on his web pages. You can go there and have a look. Okay, so now I want to tell you a bit more about what happened over the last 5 or 10 years in like unconditional results, saying here's a theory and cannot prove some statement of interest. And I will start off with the improbability of upper bounds. So let me go carefully and slowly and tell you about the motivation for this line of work. Okay, so why do we want to show that some upper bounds are unprovable? Okay, so the usual setting of complexity theory and like circuit complexity is that we have some computational problem we care about, and we want to understand, does this problem has a fast algorithm or a small circuit? So in this theory, we never talk about the actual complexity of proving that the algorithm is correct or like establishing the correctness of a circuit. So what we would like to do here is to have an extension of the original complexity theory so that we care not only about the running time or the size, but also about the complexity of showing that things are correct. Okay. So more specifically, we want to rule out algorithms in small circuits with respect to a given logical theory. So in some sense, we are relaxing our initial goals of showing lower bounds to just proving things of the following form. So here's a theory T. At least this theory cannot show that P equals NP. Okay, so for the algorithms, for the circuits that this theory can see, the theory cannot show that they will be like solving static polynomials. So in some sense, analyzing a smaller class of algorithms, only those that are somehow visible in the theory. So it's a relaxation of the original lower bound question. And this line of work was started by Cook and Krycek about 15 plus years ago. And these results are formally necessary before we prove the corresponding lower bounds. Okay? Because we're now rolling out the sufficient procedures with respect to the theory. Ideally, we want to rule out the algorithm with respect to like anything, right? Algorithms simply do not exist. We are sort of like relaxing the goal here. And okay, so let me tell you about some of, yeah.
Why wasn't there a lot of work before Cook and Krycek about this? You just need to, it's just a question of even a theory prove either unprovability or provability of lower bound or upper bound.
So this paper is specific to the unprovability of upper bounds, and they do systematic investigation of this question in bounded arithmetic. There might be previous papers that touch on this question in some sense, but I would say like this is the reference that actually explored it in like detail. But yeah, if you know more references, yeah, please.
You're talking about upper bound.
Upper bounds now, unprovability of upper bounds. Okay, so let me tell you about some unconditional results in this area. So now let's fix some integer k. Think of k as like 3. So a few years ago with Krycek, we showed the following, that the theory PV cannot prove that all problems in NP have circuits of size n to the k, this fixed k. Okay, so here's a theory can prove some interesting theorems like the PCP theorem, but we know for a fact that the same kind of reasoning won't allow us to show every problem in NP has a circuit of size NQ. And we actually show a stronger result. The theory doesn't prove that everything in P has circuits of size n to the k. For instance, let's say the Technifa graph has a clique of size 100k. That's sort of a problem. Don't expect to have circuits of size n to the k, and that's a problem in P, right? So this is like a reasonable inclusion to rule out. And so this theory cannot even show that for problems in P, they have circuits of size n. And yeah, I should also mention that there was a follow-up work that used model theoretic arguments and established the same results. There are 2 ways of formulating this proof. And a few years later, we extended this lower bounds, so this unprovability of upper bounds, to stronger theories. And in one of the cases, in a paper with Antonina and Marco, who are here, we also got some results for APC1. The nice thing about these theorems is that they are unconditional. But unfortunately, as these theories they get stronger, the upper bounds that we can rule out, they talk about very large complexity classes, right? Like ZPP to the NP with constantly many queries. And these results are actually close to unconditional lower bounds that we have. So we would like to get better results here. So that's definitely a direction where there are lots of things to, try to improve. So let me tell you very briefly about the approach we use in this last paper, which sort of gives a modular way of proving these results, okay, using sort of like a framework connected to learning. So the way we prove these theorems, they follow the same recipe. So we assume towards a contradiction that the theory proves that the problem has small circuits. So let's say APC1 shows that some problem has a sequence of small circuits. So that's a non-uniform assumption, right? For every n, there is a circuit. So you're only claiming that there is a non-uniform sequence of circuits. So what we do is kind of similar in spirit to what Madhur was explaining in his talk. So from the proof, we will actually get some computational information about the sequence. And that will allow us to actually compute in some sense the circuits, okay, in some efficient sense. And how we're going to compute them, that depends a lot on the theory. Some theories are more constructive, others are less constructive. And then after we extract this information from the proof, we are left with a question that has nothing to do with logic. We just want to rule out, in the standard sense of complexity, the existence of these constructions. And then we show this unconditionally. Okay, so that's the recipe for like all these proofs at the moment. So let me just briefly flash one result for APC1. So you don't need to read this statement, but I just want to give you a rough idea. So assuming that the theory proves some statement, here is like, for all n, there exists a circuit that is correct on every input z. And then from any proof, you're going to be able to extract some computation, some polynomial time algorithms that actually attempt to witness this existential quantifier, which is the circuit. So these are algorithms that are trying to produce the circuit in some way. And if you think about different ways of like constructing a sequence of objects, well, we have the non-uniform construction where there's no information about the objects. We have like a fully uniform, p-uniform construction. And the information we will get from these theories are in between these two, okay? It's some more relaxed notion of construction that has some flavor of learning. It's somehow trying to generate the object and you can make some kinds of queries and so on. And depending on the theory, you're gonna have like randomized learning algorithms with different types of queries and so on. And what we do at the end of the day is to show unconditionally that for some languages in P or NP, such constructions cannot exist. Okay, and that finishes the proof. So any question about this template? It was like very high level. I just wanted to give you like an intuition for the constructions.
In the end, you do some hierarchies, time hierarchy. What do you contradict?
At the end, you try to use some hierarchy, but you cannot just use that. You need to do a more complicated argument. But at the end, there is a diagonalization, some kind of indirect way behind the proofs. All right, so yeah, if you want to learn more about this particular technique, I also have a talk that covers it, so in more detail. All right, so all these theorems now you can prove using this approach. Like you start from logic and you reduce this to a question in complexity that has nothing to do with logic, and then you prove something there. And you use this learning framework. So I would like to highlight this more recent paper by Albert, Sam, and Moritz, where they show a non-probability for a stronger theory, and they show that in this theory called B02, an exp is not contained in P/poly. Okay, so you cannot show in this theory that an exp is contained in P/poly. And what I find particularly interesting is that they have a completely different approach, which is connected to the unprobability of the pigeonhole principle in some theories. Okay, so I also highly recommend for you to have a look at this paper if you're interested in this direction. And yeah, that's all I wanted to say about unprobability of upper bounds. I think it would be really nice to extend some of the results. For instance, we have a much better understanding of PV, and can we show the same improbability result for S12 and for APC1? And you could either try to use this learning template, and this will lead to some nice questions about these uniform constructions, or you could come up with a different approach. And this would be very interesting. So any questions about improbability of upper bounds?
So unprobability of upper bound, you would say give you indication of the truthfulness of the fact that there is no upper bound.
Yeah, so if you show something, some upper bound is unprovable, that means there is a model of the theory where the negation of that statement holds. So there's a model of the theory that satisfies all the theorems you can prove, say the PCP Theorem and many others. But at the same time, the upper bound doesn't hold. So you have the lower bound. So this model might not be the same as the real one, but it's close in some sense because there you can also prove many of the theorems we have in algorithms and complexity. So it's evidence for the lower bound. More questions? Okay, now I'm going to switch to improbability of lower bounds, which might be more familiar to many people here. And many people might also think it's some more interesting direction. I think both directions are very interesting. But let me now make the case for why you might care about the improbability of lower bounds as well. So we have been stuck for a long time in the field, and we have developed many explanations for why different techniques cannot lead to stronger lower bounds, like the relativization, natural proofs barrier, algebraization, and so on. So I think these are all extremely useful, but there is a sense in which they're not so nice, which is as you combine different techniques, you can easily avoid the barriers. Right? The barriers don't talk about standard notion of proof, and therefore combining different strategies, you can avoid the different barriers. So ideally, we would like to have a more robust or a more principled way of understanding the difficulty of proving lower bounds. And that's one reason for why you might want to consider this logical theories in the standard sense and try to understand which arguments can prove different kinds of lower bounds. So that is definitely a motivation, but I would say we are very far of having anything like this, okay? That, hey, here's a lower bound, it's unprovable in some theory of bounded arithmetic, and to use that in practice as a guide to which techniques we should use. So I would say this is one motivation, but at least in practice, we are very far from using it. But definitely we would like to have a better understanding of different proofs and the limitations of these approaches. Now, at least to me, I would say a more interesting direction is simply to explore this intriguing possibility that maybe the strong complex lower bounds are simply unprovable in strong theory. Okay? And I think that's a direction we should explore, we should consider. And even if, you know, the lower bounds are actually provable, I would say that exploring the proof complexity of these lower bound questions can still be beneficial. They can lead, for instance, to some class of tautologies that will be hard for some proof systems and so on. And so there are definitely benefits of looking at these self-referential questions. And we have seen this in the field, like that some unexpected results have been obtained by, you know, exploring such things. So yeah, so that's, I would say, like 3 motivations for studying the improbability of lower bounds. And at least to me, this is as interesting as the improbability of upper bounds, although they have like different reasons. So what I want to do now is a very incomplete review of the literature in this area, so that I can tell you about some of the recent results. So Sasha Razborov and Jan Krajcek in the early 90s, they initiated this more systematic investigation of the formalization and improbability of complex lower bounds in bounded arithmetic. And after this work for many years, this has been investigated both in bounded arithmetic, but also in proof complexity, like the proof complexity of propositional formulas stating like lower bounds. This has been investigated in many weak proof systems. But I will like jump right to some of the results in bounded arithmetic that will be relevant for us. So in 2015, Jan Peek, building on a technique of Krajicek, he established some conditional unprovability results in some subtheories of PV. And a few years ago, together with Rahul, they showed an unconditional result. So they show that some strong complex lower bounds, they are unprovable in PV and in a variant of APC1. So I will tell you more about this theorem and also about follow-up work where we also extended this unprovability results to APC1 and even to stronger theories, but then we have to consider even stronger lower bound sentences. So let me explain to you this line of work and this recent results. So, okay, so what Rahul and Jan consider is a sentence stating strong complex lower bounds separating NP from co-non-deterministic circuits. So in more detail, they fixed a non-deterministic polynomial time machine M. Think of M as a non-deterministic machine for SAT, for instance. And they considered a sentence depending on this machine that states the following lower bound. For every large enough input N, and for every co-non-deterministic circuit D of sub-exponential size, M and the circuit D, they will disagree on at least 1% of the inputs. So this is a lower bound for NP against sub-exponential size co-non-deterministic circuits on average.
How is epsilon quantified here?
For no epsilon, you'll be able to show the lower bound sentence. So they prove that no matter which machine you start with, this sentence is not provable in PV and in a variant of APC1. Okay, and what's really nice is that this is a non-conditional result. So you know for a fact that this very strong lower bound is unprovable.
So what is?
Yes. What's okay?
They fixed. M is fixed.
Yeah, so for every machine M, you write down a sentence saying a strong lower bound. No matter which machine, this is going to be unprovable in the field.
What is the difference between the co-non-deterministic size and co-NP?
Yeah, so these are non-uniform circuits. Yeah, that's the difference. More questions?
What's the fragment of APC1?
It's APC1, but you restrict the dual weak pigeonhole principle, so it doesn't have extra parameters. More questions? Okay, so then last year we extended this ideas to APC1, and we showed that APC1 cannot show strong lower bounds separating the third level of the polynomial hierarchy. So in some sense, taking this original result, which was for NP versus co-n size, lifting it to a higher level of the hierarchy, but now we can show unprovability in the standard definition of APC1. So more precisely, we have a sentence saying that polynomial size pi3 circuits cannot be approximated by sub-exponential size sigma 3 circuits. So this is like the non-uniform analog of the third level of the polynomial hierarchy. And you can formalize the statement in a natural way. The circuits, they are just like standard circuits, but they have extra inputs for the non-deterministic gases. And yeah, formally we show that APC1 cannot show this lower bound sentence. So this is like a single lower bound sentence as opposed to the previous work of Rahul and P, because now everything is non-uniform. And yeah, so now we have a theory that can prove some very weak lower bounds, like monotone lower bounds, bounded depth lower bounds, but at least some very, very strong lower bounds we can also show they are unprovable in the field. And of course, there's a huge gap between what it can do and the unprovability results. We would, of course, like to bridge the gap if possible. Okay, so let me, in 1 minute, tell you about the strategy for this proof. So we build on the Peek and Santana unprovability result. The challenge now is that we have a stronger theory, and the quantifier complexity of this lower bound sentence is also higher. It talks about third level of the polynomial hierarchy. So this is similar in spirit to you know, going from depth 3 circular bounds to like depth 5 circular bounds, okay, in terms of like analyzing what's going on. So it's a little bit more challenging. And we argue by contradiction. So suppose APC1 does prove the lower bound. And again, we're gonna use some kind of way of extracting computational information from the proof. And from the proof of the lower bound, we will actually derive some algorithms. And we're gonna use these algorithms to give a corresponding upper bound. And it turns out that the lower bound and the upper bound, they are in contradiction. So that's how we sort of diagonalize. And that shows that the original sentence is unprovable in the field. Yeah, so I won't have time to tell you more about this, but there's also an online talk giving like many more details about the proof. Okay, so any questions so far? This was a review of some of the results from the last 5 or 10 years. Yes?
Should we see this as evidence that the strong lower bounds maybe do not hold, as you do for the upper bound, rather than saying that they
Yeah.
are not?
Yeah, that's definitely a valid interpretation. So some people might say, yeah, so maybe this is evidence that we actually have upper bounds because the theory is so strong and can prove so many things. So yeah, that's totally valid. I guess we have maybe bias in the field to always think about the lower bounds holding. More questions, yes.
Oh, I'd like to ask, what are the most notable things that can be proved by PV and APC1?
You want to know some examples of
Yeah.
results? Okay, so APC1 can prove everything that PV proves. So APC1 can prove the PCP theorem and many of the weak circular bounds we already know. More questions? Okay, so I have maybe like 10 or 15 minutes. So I want to tell you about this recent paper with Li Chen and Jatuli. And the main motivation here for us is we want to understand the improbability of much weaker lower bounds, right? Not like third level of the polynomial hierarchy in some very strong sense. And yeah, so, and then we started this project with this goal of at least moving from like average case lower bounds to worst case lower bounds. And hopefully like talk about even simpler lower bound sentences. So that was the main motivation here in contrast to these previous papers. And so let me tell you about what we do. So we studied what we call the reverse mathematics of lower bounds. So what we want to do here is to actually understand exactly which kind of axioms we need to prove simple lower bounds. So how we study this question? So we're gonna fix some very weak base theory T, or as this base theory will be PV. So this is a theory that we believe cannot prove some lower bounds at least. So this will be the base theory. And then what we want to do is to establish that over this base theory, the lower bound sentence is equivalent to some combinatorial principle. Meaning that I can prove the lower bound if I use this basic theory and the principle. So the principle is sufficient to prove the lower bound, but we want to show it's actually necessary. Okay, that any proof you have of this lower bound and this base theory, we'll have to use this combinatorial principle. Okay, so we can also derive the combinatorial principle from the lower bound in the base theory. Okay, so these two statements are equivalent over the base theory. And if we could do that, that means we have a much better understanding of the lower bound sentence. And more important to us, we already know that some principles are unlikely to be provable in PV. So if we can now establish the equivalence of some lower bounds to these principles, then we derive that the lower bounds should also be unprovable in PV. So that's also one of the main motivations. Okay, so which principles? So we be looking at the different pigeonhole principles. So these are the principles already familiar to most of you. So we consider the standard pigeonhole principle, the dual weak pigeonhole principle, which is the one I introduced for APC1. And yeah, those are the pictures representing the principles. And we also look at this so-called witnessing pigeonhole principle or retraction pigeonhole principle, which says that if I have two functions f and g, one is compressing and the other is decompressing, then this cannot be the identity function. Okay, so that's the witnessing pigeonhole principle. And we will consider these statements for polynomial time functions. So for every f in the language of PV, we have a principle. In fact, we'll be looking at the weak versions of the principles. So in the weak versions, the sizes of the domain and codomain, they're not different by one, but by some slightly larger quantity. Those are the weak principles. And for a technical reason, in one of the results, we will forbid extra parameters in the principle. So the way these principles are usually employed in bounded arithmetic is that you have some function f, and you can take more parameters. And the principle will actually postulate that for every way of fixing the second parameter, now I get some function, and it satisfies the pigeonhole principle. So that's the usual way of using these principles in bounded arithmetic. All these axiom schemes, they come for functions with several parameters. For every way of fixing all the other parameters, the resulting function satisfies the principle. There will be one result where we will forbid these extra parameters. And in that case, I will use this prime in the principle. It means no extra parameters in the axiom. Just a technical point for the specialists in the audience. Don't have to worry about it. So any questions about the different principles? Okay, so we have two sets of results. The first are the equivalences of lower bounds, some combinatorial principles in the base theory, and then we derive several consequences of this equivalence. So let me first tell you about the actual equivalence. And we're gonna have theorems for the weak pigeonhole principle and the retraction pigeonhole principle. So this is the one we established for the weak pigeonhole principle. We show that the following statements are equivalent over PV. The first is the weak pigeonhole principle for polynomial time functions. The second is showing that the equality function requires communication complexity n. So this is the two-party deterministic model of communication complexity. This is also equivalent to showing a weaker lower bound of n to the epsilon, and just for one-way protocols. And this is also equivalent to the singleton bound for error correcting codes. Okay, so over the base theory, this pigeonhole principle is equivalent to communication complexity lower bounds and also to some combinatorial statements for error correcting codes. And in particular, you get the following from this equivalence. You get that if PV could prove weak communication lower bounds for equality, just for one-way protocols, then it actually proves like the optimal communication complexity for protocols with any number of routes. There's some kind of amplification phenomenon happening in this bounded arithmetic theory. Okay, so yeah, I'm not telling you how to formalize this. This is like just an informal statement, but that should be sufficient for me to at least give you some intuition for this proof. So let me try to explain to you the connection between communication complexity and pigeonhole principles. Okay, so let's try to sketch the proof that the weak pigeonhole principle is equivalent to communication lower bounds for equality. So everything we do, we're doing in the base theory PV. So let's start with the implication from 1 to 2. Okay, so now we assume the pigeonhole principle and we want to prove a communication complexity lower bound. And for this, we're just going to follow the usual proof of communication complexity lower bounds, okay? So we consider a polynomial time function that we take a protocol as the extra parameter, and will be a function of the first parameter x. And we compute the following. Given x, we generate the transcript of the protocol on x, x. Okay? And now, if this protocol has communication complexity less than n, there will be a collision, right? So we have now that there's a pair of inputs, x, x, and y, y, that generate the same transcript. Now we apply the full set technique to reach a contradiction. Okay? And for this final step, you need to do some proof by induction, right? What happens to the protocol as you're running it with different input pairs. And that can be done in PV because we can do induction for polynomial time predicates on the binary notation. And the binary notation here is like the bits of the protocol. So that's how you prove communication complexity lower bound from the pigeonhole principle in the base theory. Now, let's see the other direction, which is slightly more interesting. It's also very simple. So now we want to show that any communication lower bound has to use the weak pigeonhole principle. And we do this in the contrapositive. So let's suppose for some function f, the weak pigeonhole principle fails. So this means that there's some way of fixing this extra parameter in the function such that now you have a map, say from n bits to n-1 bits that is like a perfect map. So there is no collision. Right? And in other words, we like perfectly compressing n bits to n-1 bits. And we can use that to design a correct protocol now, because that's what we want to check. Like if x is equal to y, I send you an exact version of x, and the other player can just check. Okay, so the failure of the pigeonhole principle gives a compression scheme, and that gives a better protocol. And that finishes the proof. Okay, so that's how we can think of the pigeonhole principle as some kind of communication complexity lower bound. All right, so I don't have much time, so let me just mention what is the most interesting result of this paper. Now we're going to be looking at this uniform version of the weak pigeonhole principle without the extra parameters. And we are interested in equivalences between this pigeonhole principle and uniform complexity lower bounds. And because we're in the uniform setting, that's why we won't have these extra parameters. So you can think of them as like some kind of non-uniform advice. Okay, so we're talking about the weak pigeonhole principle without extra parameters. And we show that over PV, this principle is equivalent to showing single-take Turing machine lower bounds for the palindrome language. It's just the classical Turing machine lower bound. And again, here we get this amplification phenomenon, which is PV proves a weak form of the lower bound, if and only if it proves the optimal lower bound of n squared. Okay, so let me now briefly tell you about this proof. So how we connect this principle to Turing machine lower bounds. So let's sketch the proof of the equivalence between the two. So let's first go from 1 to 2. So now we want to show Turing machine lower bound using the weak pigeonhole principle. And the intuition comes from the previous proof, right? That the pigeonhole principles, they are essentially equivalent to communication complexity lower bounds. And it's known how to show this Turing machine lower bounds by a reduction to communication complexity. Okay, so you need to be slightly careful with which proof you use, because some of these proofs reduce to randomized communication complexity. But if you're careful enough, you can also reduce the deterministic communication complexity. Okay, and that's how we go from 1 to 2. That's sort of like the intuition. So we can prove Turing machine lower bounds because we can prove communication lower bounds. Now, the most interesting direction is how to go from 2 to 1. So if you could show single-take Turing machine lower bounds in PV, why do you need to prove weak pigeonhole principle? And again, we're going to argue in the contrapositive. So let's assume that the weak pigeonhole principle fails for some function f. And again, we want to use this f as some kind of perfect compression scheme. Okay, so it's mapping n bits to n-1 bits in a perfect way. And it turns out that if PV can have access to such a map, it can iterate the map, and it can actually compress n bits to n to the epsilon bits in a perfect way. So that can be done in PV. Okay, so great. So now we have this compression from n bits to n to the epsilon bits. That's a perfect compression. It can be done in polynomial time. And what we want to do is to show this implies that there is a single tape Turing machine that solves palindrome in less than n squared time. So here's the plan. What we want to do is we try to decide palindrome. So we want to compare the first half of the string to the second half of the string. And the idea is we're going to hash both parts. So we now have just n to the epsilon bits, and then we'll try to compare the two hash values. Okay. Because now we have a much smaller input, then it will be easier to program the single tape machine. Now, the main issue with this plan is that we started with some perfect compression scheme, but it's computed by some arbitrary polynomial time function. Okay? That's not a single tape Turing machine running less than n squared time. So that's the main barrier for this proof to go through. And the way we solve this problem is by incorporating an idea from cryptography called the Merkle-Damgard construction. It's a technique that allows you to improve both the shrinkage and the running time of collision-resistant hash functions. So using this technique, you can actually move from a polynomial time hash function to one that runs in time n to the 1 plus epsilon. And now what we do is we take this technique and we show how to implement it in a single tape Turing machine in less than n squared time. And additionally, you need to show that PV can understand everything that it's doing and that it can formalize the correctness of this. That's what requires a more careful construction. And that finishes the proof sketch. That establishes the equivalence between the weak pigeonhole principle and single tape Turing machine lower bounds. Okay, so I don't have much time, so let's leave questions to the end of the talk. So I'll briefly go through some consequences. So now that we have this equivalence between single tape Turing machine lower bounds and the weak pigeonhole principle in the theory, we can just rely on some previous cryptographic hardness to show, because the weak pigeonhole principle shouldn't be provable in PV, then even this very weak Turing machine lower bound shouldn't be provable in PV. So in some sense, this goes against the intuition from some of these previous papers that most lower bounds could be done in like PV or in APC1. So in particular, under the existence of collision-resistant hash functions, even the single tape Turing machine lower bound cannot be done in APC1. We also have an equivalence for the retraction principle. And here the difference is that instead of considering the equality function, the equivalence holds for the set disjointness function. And we can only get equivalence to single round protocols. So single round protocol lower bounds for disjointness, they are equivalent to the retraction principle over PV. And that gives us a sort of nice consequence, which is a fine-grained understanding of the reverse mathematics of lower bounds, which is the following. So this retraction principle is actually provable in APC1. That is a known result. And that's equivalent to set disjointness lower bounds. So this set disjointness lower bounds are provable in APC1. But if you use the previous conditional results, because equality lower bounds are equivalent to weak, which is supposed to be unprovable, then we get the communication lower bounds for equality are unlikely to be provable in APC1. So we get this refined or fine-grained understanding of for which functions we can hope to prove lower bounds in APC1 for communication protocols. And just to finish, here's some open problems. It would be nice to understand what happens to multi-round communication lower bounds in when you use the retraction principle. We don't have this understanding yet. I think these results might allow us to get a better understanding also of the difficulty of showing like lower bounds with respect to different sizes. For instance, can we capture near quadratic formula lower bounds by some principle and show that if you want to go from n squared to n cubed, it's actually harder in some proof complexity sense? And what happens beyond n cubed? Can we somehow show some equivalences? And with respect to the first part of the talk, the results we have right now, they are weak. It would be nice to extend them to stronger theories. for instance, the things we can do for PV, can we also do for S1 too? And I think this leads to some nice technical questions about different witnessing principles for PV versus S1 too. And yeah, so this is just a diagram from the paper of all these equivalences we established. And the paper is also on my website since last week. So if you're interested, go and have a look at it. And thank you.
Questions?
Yes.
So because you have the equivalence between probability of palindromes and a pigeonhole principle, can you get circuit lower bounds from the one-tape Turing machine bound?
That's not something we explored. It's an interesting question.
Antonio?
How does this connect to the indistinguishability of obfuscation assumption?
Yeah, so the conditional and probability results we have, they only need the existence of collision resistant hash functions. I'll say it's a weaker assumption than the obfuscation. More questions?
Well, what is the best evidence that we have for thinking that the parameter-free and parameter version of injective PHP are distinct?
I think in this paper of Giotto and Rahul Longo, they give a conditional result saying these are distinct, but I don't remember the details now.
Question, sir, can you go to slide 35? Okay, so here conditionally, APC1 cannot prove this very simple communication complexity lower bound. On the other hand, you told us that the APC1 can do circuit lower bounds like bounded depth circuits. I think I know the reason why this happens, so maybe you want to comment on it?
Okay, maybe let me comment. Yeah, so that's the mathematical results, right? We cannot dispute them. But I think it really tells us that we should revisit this intuition about the power of APC1. So if we want to say we have like a robust theory and we have strong results showing like things that can be done in the theory, if we want to interpret that as something in practice for us, we need the theory to be much stronger than APC1. There are like these very, very simple results that probably can be done in APC1. So we should at least consider APC1 plus the weak pigeonhole principle, and like try to show these previous unprobability results with respect to this new theory, sort of accommodate these deficiencies. Okay, but like I mentioned in the beginning of the talk, I think we're still trying to figure out what would be like the best theory T that could be like meaningful enough for us to say, once we show something is unprovable in T, that really means we will need like completely new ideas. Yeah.
I mean, maybe this is like a little bit of a crude way of summarizing it, but like it seems like APC1 probably just can't implement like these sort of basic counting arguments, right? Like so for example, maybe to say it a different way, like could you, maybe it would also be possible to prove it can't prove things like Nechaporek's lower bound?
So APC1 can do approximate counting, so it can approximate probabilities. You might not be able to do exact counting.
Exactly.
So it already does a lot of probabilistic combinatorics. I would say it's really about the fact that the pigeonholes is like collisions, and that finding collisions should be hard.
Oh, okay.
So I would make a distinction between that and like approximate counting. Marco?
What is the nicest upper bound for that palindrome result in terms of the theory? Do you have like a nice theory you can put it?
APC1 plus dual weak pigeonhole.
You don't actually need APC1.
Yeah,
right?
Yeah, that's the best of them. And that's actually
Tight.
Yeah.
Yeah.
Okay, so thank you very much for your talk.